Let's see how we would use alternate, universality of NAND and NOR. So in this question, I'm asking us to take this circuit. The circuit is A and B or C and D, and replace it with just NAND gates. So I wrote a bit of the answer already. It's that we need to look at the original circuit. So the original circuit looks like this. There's A and B, so that's here, ORed with C and D. So ORed with C and D. So I wrote out the original circuit, but the question is replace this original circuit with a circuit that is only made up of NAND gates. So how do we do that? Well, we're first going to, let's look at the OR section. So here's the OR section. Well, how do I represent OR with just NAND gates? So we look at our cheat sheet, which you can have in front of you for the final exam as well. And for the rest of all time, you don't have to memorize this. You don't have to memorize it. You just need to know how to find it. So an OR gate looks like, oh dear, it's the big combination here. So this is the OR gate that we need to replace with. And then we want to replace the AND gates with this, which is also kind of a large combination. So this circuit is going to look a lot bigger. Let's do the OR gates first. So the OR gate, instead of this tiny little OR gate we have here, it looks like what I just looked up above. So it looks like a NAND. Of course, I'm replacing everything with NAND, so it better look like a NAND. And then it had another NAND and another NAND. And you don't have to memorize this. We just looked it up. So, and then these inputs were connected to themselves. And that's what an OR gate looks like in universality of NAND and NOR. This is equivalent. So this OR gate here is the same as this OR gate here if you were to do the truth table. And now let's replace this part that is an AND. And we saw that, well, that's a bit of a pain to replace as well. It takes some time, but it's worth it. To do that, of course, it's a NAND because that's the point, is that we're replacing AND with NAND. And those inputs were connected together. They were connected to another NAND. And A and B would go into that NAND. So that's this one. And then, of course, this one is going to be the same, right? So let's draw it again. But that one has C and D going into it. So now I've answered the question. I've replaced the circuit with just NAND gates, but never leave it like this, please. The whole point of replacing things with NAND gates is to make it as small as possible. So I'm going to ask you then, what is this? It's the same as this. The two inputs are, the same thing, the same signal. It's one signal going in twice through an AND gate. This is the same thing, and this is the same thing. So what are they? So again, you don't have to memorize it, but once you do a few example problems, you will accidentally memorize it. And look at that. That's this thing. What's that thing? That thing is an inverter. Cool. So I have 4 inverters. That's pretty neat. So I have 4 inverters. So would you ever put an inverter in a circuit and then invert it again? So if you put a 1 in, it would become a 0 here, and it would be a 1 out. If you put a 0 in, then it would become a 1 here, and it would become a 0 out. So what if I just got rid of those two things? Then I'd have a 1 connected to a 1. So do I really need those 2 inverters? No. What if I just had the 0 connected to the 0 and I got rid of both of those? So what I'm trying to say is they essentially cancel themselves out. So anything that looks like this is an inverter. So these two essentially cancel themselves out. These two essentially cancel themselves out. So your final answer is then you get to keep these two NANDs. And that's A, B, C, D. And they went into another NAND. This is NAND, NAND, NAND. And there's your answer, X. So why did we do this? Does this make us happy? Well, I used to have 1, 2, 3 logic gates. Now I have 1, 2, 3 logic gates. So this is the answer. Great. Well, you're going to say, well, why on earth would you have wanted to go to that trouble? They look exactly the same. Well, the reason you go to that trouble is how many chips do you have to take out of your toolbox to build this circuit? You have to take an AND chip out. There's your AND chip. And then you have to take the OR chip out. Whereas how many do you have to take out of your circuit to build this? Just your NAND chip, right? It's got multiple inputs. It's probably quad or, yeah, it's probably a quad NAND. So I can build this with 1 chip. And this was 2 chips. And that's not too much more expensive for you because you're only building this circuit once, but it's pretty expensive if you're making 50,000 of these devices in a day. So this saved us money and that's a good thing. So this is a simplified circuit that costs less money to build. And that's the point of universality of NAND and NOR. This has been an example of universality of NAND.